Welcome to Mineral Talks Live, the monthly live mineral webinar that brings you in-depth and in-person interviews with mineral people from around the world. Mineral Talks Live is brought to you by a joint effort among the Mineralogical and Geological Museum at Harvard University, the SMMP, and Blue Cap Productions. Tune in on the first Wednesday of every month and stay connected to your mineral world. Now, broadcasting live from beautiful Honolulu, Hawaii, the land of aloha, ukuleles, and shakas, this is Mineral Talks Live. Welcome to Mineral Talks Live, the #1 mineral talk show on the internet. I'm your host, Brian Swoboda, and on behalf of the entire Mineral Talks Live crew, we're really happy you could join us today. Speaking of the Mineral Talks Live team, I represent only 1/3 of our merry little gang. The other 2/3 of our team includes Dr. Raquel Alonso Perez from the Mineralogical and Geological Museum at Harvard University, and Dr. Eloise Gaillou from the Society of Mineral Museum Professionals, also known as the SMMP. As you can see, Mineral Talks Live is a majority female-owned endeavor, and that's really important to me, especially with today's guest, who we'll get to in just a moment. For those of you tuning in for the first time, Mineral Talks Live is a monthly mineral talk show that airs live on the first Wednesday of every month. Our goal has always been to connect you with other members of the mineral collecting community via our interviews with some of the best curatrix, curators, collectors, dealers, miners, researchers, artists, and media people in the mineral world. If you happen to have missed any of our past interviews, don't worry, your pretty little heads. You haven't missed a thing. There's a complete list of all those episodes along with links to those interviews at the URL located at the bottom of the screen. One of the things that makes this program unique is that not only is this a live show, but it's a show where you get to interact with our guests. All you have to do to participate is to type your comments in the chat or the Q&A features, both of which are located at the bottom of your Zoom window. The chat feature allows you to instantly send messages to everyone watching the live show, so we encourage you to be as active as you'd like in the chat while we're talking. And while our guests and I generally don't see your messages during our conversation, throughout the show, both Raquel and Eloise, although today it's just going to be Raquel because Eloise is tripping the light fantastic somewhere, we believe in Asia. So Raquel will be monitoring the chat area and will be very active there. Occasionally, she may even interject a question or comment to us during the interview. So don't be shy if you want to ask something. Also, when you log in, we ask you to send a message to everyone on the chat, letting us know where you're tuning in from so that we can see how far around the world we're reaching. If you happen to have a question directly for our guest, or maybe it's a bit more detailed and needs a bit of a longer answer, go ahead and use the Q&A feature and we'll get to those questions at the end of the show. Finally, towards the end of the program, you'll see a window pop up on your screen. This is our quick fire 5 questions segment to see how well all of us know our guests. It's just a little fun way for us to get to know our guests a little better. So go ahead and play along our little reindeer game. This can be a great icebreaker when you see our guest at the next mineral show. Now, today's guest is not only a brilliant scientist, teacher, researcher, geologist, field collector, award recipient, lecturer, author, advisor, racer, and runner, but our guest is also a woman who is a strong advocate and supporter of other women in our field. From the very first time I've met her, I've been impressed by her, and she's been an inspiration to the other Mineral Talks Live team members as well. If you look at her 45-page resume or CV, yes, 45 pages, you'll see how superhumanly busy she is, which explains why it's taken us until episode 87 to finally get her to join us. Ladies and gentlemen, please type in a huge greeting to today's guest in the chat window, Dr. Barbara Dutrow. Barbara, how are you?
Thank you. Thank you so much for having me. And thank you for your patience. And the many times I said, oh, please later, please later.
Well, Barbara, it's patience and persistence. And I'll tell you, it worked out because you're on the show now. I'm just so thrilled that we're finally able to get you. I know it's been a crazy time with your schedule and everything. So really, thank you immensely for joining us today.
And to all of you for putting this on. So,
our pleasure. Now, Barbara, I always start the interviews, kind of getting a little bit of background on our guests. And I simply love a good origin story. And I know your story will be fascinating to me as well as all the young women collectors out there. Tell us how you first started getting interested in minerals.
So it's actually fascinating to me that I was one of those very lucky people who just adored minerals from as long as I can remember. So as a kid, I would pick up rocks and minerals. And when I was very young, I grew up in the middle of the sand hills in Nebraska, well, actually, till age 5. And then my folks moved from a small town of 500 to a slightly larger town of 5,000 in northwest Nebraska. But in between, we went on a trip to the West Coast. So we went through Arizona, New Mexico, California. And I was about 5 at the time. And I picked up rocks and minerals along the way. And my mother would always tell the story that I put the rocks and minerals in one side of the car and my dad would throw them out the other. So that was kind of how I began. We always had a rock pile in the backyard of the house. So that was the very beginning.
Do you remember what quality about the rocks that you first picked up really kind of piqued your interest?
They were just fascinating pieces of the earth. I loved the out of doors. We spent a lot of time hunting and fishing and camping and being outside as kids. And I loved the textures, the colors, the feel, and just what they were.
Well, now here we have a very, very young picture of you. Lovely picture. And so my question, who's that young girl standing in the picture next to you?
Exactly. It's my cork gun. So my dad was quite the outdoorsman, and he took us hunting and fishing, as I said, as kids. So he had a goose blind on the North Platte River in the middle of Nebraska. It was on the North American Flyway. And we loved eating ducks and geese. And there is Mr. Canada standing next to me. And clearly I was very good with my cork gun. But the best part about, yeah, exactly. The best part about this, which you'd spend all weekend sitting in this goose blind, freezing, because it was, of course, Nebraska in the winter. But afterwards, you were rewarded with some kind of treat. Now, most people would take, a stuffed animal, but there was a rock and mineral store in Llewellyn, Nebraska, and I wanted a mineral. So that was one of my first minerals. I bought a small amethyst, which was purple because I love purple, and it's my birthstone also. So that was one of the first purchases of a mineral that I can recall.
Oh my God, I love it. So you were totally invested in the outdoor. And I love that because the way that you describe the qualities of the mineral that you were fascinated by as a youngster seems like that is kind of paying forward into your life now. The terms that you use are exactly the terms that you would use, that I would expect you to use, talking about why you're interested in minerals now.
It's absolutely true. I mean, I collected tadpoles, but I was really surprised when they grew up and hopped out of their cage, and grasshoppers, but they weren't nearly as interesting. But I think another. Sorry.
Sure. Go ahead. No, go ahead, please.
No, I was going to fast forward through to 8th grade.
Oh, well, and this question may play directly into that. So as a youngster collecting minerals on one side of your car while your father's taking it out on the other side, what was the next evolutionary step in your involvement in the mineral world?
So I think my father made me this beautiful bookcase because we loved books too. And then I could have a place to display my minerals. So I had books and I had minerals. And then I had the great, wonderful fortune of having a phenomenal earth science teacher in 8th grade. Now, this, mind you, is in a small town in western Nebraska. And it was a public school, but teachers do make an enormous difference and impact on your life. And she was just phenomenal. She taught us about the earth. We took field trips as kids, as eighth graders. And at that point, I decided I was going to become a geologist. And I never wavered. I was absolutely determined to be a geologist, even though I had absolutely no idea in eighth grade what you could do to make money as a geologist. So that was the next.
Barbara,
path.
That's eighth grade. That is extremely early in a life cycle to decide a career for yourself. That is amazing. And it's even more amazing that you not only created a career, but an incredible career on that.
My parents, of course, had absolutely no idea if I could they didn't understand geology. It was a very blue collar town, and it was fabulous. I managed to make a career out of the things that I'm most passionate about. And I think they encouraged that passion. My dad was a very passionate mechanic, and he ended up being a car dealer, and he loved cars, and that was his passion. So he allowed me to follow it no matter where it led.
Oh, I love it. I think your parents were extremely wonderful examples of being great parents that encourages the interests of their kids. And the fact that they gave you that liberty is fantastic. I love that you were able to do that. I'm going to pull up a picture, and I'd love you to talk about this, because it's rock based. It's not mineral so much as collecting, but you're standing. Well, tell us about this.
Yeah. So I had a 4-year scholarship to go to a state college in Nebraska, and there was only one that offered earth science, and that was Chadron State College. So, of course, since I was going to become a geologist, that was the place I went. And we had, again, wonderful, committed geology professors that engaged undergraduates in research. Now, in western Nebraska, there's a lot of sediments. We were close to the Black Hills, which is a fantastic mineral collecting area, but they did a lot of vertebrate paleontology research. So one summer, just as I started college, we were called to Hot Springs, South Dakota, where they had discovered it looked like the tusks of a mammoth. So he took a bunch of undergraduates up to Hot Springs, and we began excavating. And I found this mammoth skull. We found, it was the housing development. And so they had just scraped across the tusk, and it turned out the top of the skull with a bulldozer, and realized it was something magnificent, and called in the research professors. So then I spent time working at the Hot Springs Mammoth Site, which is now a national natural history area.
Well, thank God we didn't lose you to paleontology. I mean, I love that you stuck with the minerals. And it was about this time, and I'm going to pull this up, that you made your first serious mineral purchase. And this is from World Minerals, but David New. And this was incredible, because this was a tourmaline that you bought. This was in what I want to say, 76. And little did you predict how important tourmaline would become in your life. So kind of give us a little backstory here.
So I think I must have learned about David New from one of the other geology majors at Chadron. So it was interesting. David New sent out paper copies. They were basically basic catalogs of minerals, and you could choose your mineral, either call him or send him a letter, and then he would send you the mineral on approval. And I love tourmaline, and it just so happens that I bought my first, and here it is,
I love it.
this doubly terminated tourmaline, and you can see the beautiful asymmetric morphology with plus C and minus C, and the crystal, how it's nicely colored zoned. And this was from the Himalaya mine. And
Yeah.
I think even back then, when I just did the recalculation of what the 1976 dollars would be. And I can assure you that tourmaline were just as expensive back then as they are now.
Right. Well, it shows here that that piece was $75, which, that wasn't cheap.
Yeah, it wasn't. I think my folks were quite upset that I was spending money on tourmaline as opposed to saving for college. But I was in college, so I was doing the best I could. I worked my entire college career. So that was David sending me the note and then thanking me for my purchase. And then, of course, I continued to buy from him because that was the only way we could purchase minerals.
So this was another purchase, a topaz.
It is, and it was. So here is that one. You can kind of see.
Oh my God.
It's, I had no idea what I was buying, right? We had no mineral mentors, so to speak. So this was, it just has it's beautiful in euhedral on the front. It has a nice termination, but it's quite rough on the back. But that was one of my other minerals that I purchased from David New. And as you can see, I tried to upgrade my collection, but I still have all of my favorites from the past.
Well, now, do you remember the description of either one of those pieces that was on the typed list that David would send out that intrigued you enough to say, that's the one that I want? Because you didn't have any imagery of it, right?
No, right, correct. There was no imagery whatsoever. It was just a description. So usually his descriptions were very much, here's one of his, they were short. I have one of his latest catalogs. They were short. They told you the color, they told you the shape, and they told you the size and the price.
Barbara, do me a favor if you wouldn't mind. Could you actually read like one of the listings there to us?
Let's see. Platinum, polybasite, speen. Oh, here's a speen from Minas Gerais, Brazil. Select pale, olive green, slightly etched twin crystal specimen. 3 1/8 by 1.5 inches to 1.5 by 3/4 inches. 10 specimens, $7.50. 20 specimens, $12.50, or 50 specimens, $20.
Oh my God.
That was one.
That was so typical of the time. I know Donna Light's watching it, so she was, Cristalli was very active back in that time, and they probably did similar things. But it seems so alien nowadays with technology where you get videos of these things live to purchase something based on a description like that.
Right. And so to me, a blue topaz was spectacular. I knew topaz from the imperial color. I knew their crystal form. I had by now a mineralogy class in college, and I was able to TA it even as an undergraduate, which was really fun. And I'm sure that it was the crystal form as well as the color, certainly for the tourmaline, was a double termination.
I love it. I love it. I've got another. Tell me about this time in terms of your career and what was going on here.
So during my PhD, then I went from Chadron, Nebraska, and I fortunately had a teaching assistantship to go to graduate school because I'm still, totally determined to become a geologist. And so I went to Dallas, Texas, to Southern Methodist University. And there they had a phenomenal metamorphic petrologist. And this was during my PhD. I worked in Western Maine in the Farmington Quadrangle, collecting metamorphic rocks. And this was a non-buggy area. Now, mind you, Western Maine, as you all know, in the summer is filled with black flies. Mm-hmm. So we were trying desperately to find rocks that we could be relieved from black flies for just a small amount of time. So here we are at just collecting with a sledgehammer, I believe, metamorphic rocks containing starlite in one of the streams near Farmington Falls. And it was great at that time. I also did experimental work as well as field work and analytical work. But the field area in Maine was very close to Mount Mica and the Newry mine.
Oh, fantastic.
So my field assistant and I would work very hard during the week, and then we'd take weekends off and go to the Newry mine. And there I met Dean McCrillis, for some of you folks from the past, and he ran the Plumbago Mining Company, and they mined tourmaline. Now, by now, I was just a fan of tourmaline. And I bought a couple of cut stones from the Plumbago mine, and this is one of them. Superb. So it's a blue tourmaline from Dean McCrillis at the Plumbago area.
I love it. So, Barbara, let me ask you this. It almost seems like tourmaline was destined to be part of your life. In '76, you bought that Himalaya tourmaline from David New, and now you're doing your PhD in your stone's throw from the Maine tourmaline fields. Do you recall when tourmaline first kind of entered your consciousness, how it entered your consciousness, how you were introduced to tourmaline?
I remember, again, seeing the crystals and how phenomenal they were with the color zoning, the form, the morphology. And then during my PhD, I had again, metamorphic rocks. There were some starlites that had been replaced by both muscovite and tourmaline. And that was just phenomenal because it was like a marriage of my two favorite minerals.
Super.
So I remember then at that point, I just loved tourmaline. The color, the character. It seemed Fantastic. To embody just phenomenal complications and depth.
Mm-hmm. No, okay. So after, I think right when you were going for your PhD and looking at your CV, you were first, was it first a teaching assistant and then a research assistant? And so it seems like both of those roles played very important parts in your life. Let's talk a little bit more about the teaching assistant part of it, and then maybe we can get to the research assistant part of it, because those went quickly from assistant to kind of lead teacher. You have so many credentials on being a professor, but also being a researcher. So let's start with maybe teaching, and you can tell us a little bit about your background from when you're doing your PhD onwards.
So fortunately, a lot of graduate students we fund through teaching assistantships, and it's a marvelous opportunity to interact with, students, the next generation of scientists. And I had that opportunity to interact with the mineralogy class. So I've taught mineralogy since, I'm giving away my age, but since the early 80s. But everybody knows anyway. As a runner, you always do things in age groups, so absolutely everyone knows your age. So it was a wonderful opportunity to teach the students about mineralogy. So I've been involved in teaching mineralogy class or mineral sciences, however you'd like to describe it, since that time. And you can also hone your skills at interacting with the students, and you can also, when you're teaching something to someone else, you learn it yourself. It's like they say, Exactly. You learn algebra and calculus class, and you learn calculus and differential equations. It's kind of the same thing. Absolutely. But it was a wonderful time to be able to interact with the students. And then we took them on a lot of field trips also. So doing field work has always been important.
Well, I know that one of the field trips that you were doing a lot with students was here in the Sawtooth Mountains. Let's talk about some of the work that you're doing here.
Yeah, so that's some of my current work and I always incorporate students, both undergraduates as well as graduates, in my field work as well as my lab work. So the peak to the left, that's the highest peak in the range. It's called the Thompson Peak, and it is in the Sawtooth Mountains. It's near Stanley, Idaho, just north of Sun Valley. So we've been working up there for the past several years, not in the granites that have some of the spectacular aquamarines, but in smoky quartzes, but we're here in the metamorphic rocks that have minerals that tell us about pressures and temperatures deeper in the earth. So we're trying to understand more of the tectonic evolution of the area and calculating, how deep were the rocks buried? When did they surface? Do they represent some of the older parts of the continental crust? And of course, also, if you live in Louisiana, you do want to escape Louisiana in the summers. And hiking to 10,000 feet is a good way to do that.
Sure. Especially if you get to come onto beautiful lakes like this.
This is it. So actually, if you look straight up, this is called Goat Lake, and this is part of the areas where we have camped. We have to backpack in because it's all the wilderness area. So we pack in for 3 to 4 days at a time and then pack all of our rocks back out. These were some of my graduate students and students that went from sea level up with me. We spent some time training to be able to hike up to those elevations. And it's about a 6-mile hike in over the glacial moraines. So if you look back into the valley, you can see Thompson Peak in the distance. But these are some of the areas where we spend time in the summers. So these are 3 of the graduate students that I've had, and 2 of them actually work for oil companies now. One's at ExxonMobil, one's at Chevron, and one's working on her PhD.
Superb. And then this is definitely a nice way to spend a summer.
It absolutely is. So this is close to just the base of Thompson Peak. You see the lake that's down to the left, and then you see the valley that's about 4,000 feet below us. That's the Stanley Valley. So it's often a challenge to when you get into the field because there may be too much snow, too little snow. It's easier to walk across the snow as opposed to the talus, but it also covers up a lot of the rocks. So we end up doing a lot of snow moving across snow also, which is unusual for the students from Louisiana.
Well, I love it. And then this one, it's kind of like cue Sound of Music here.
It's true. These are some other of my graduate students, and we're hiking in. They're all doing theses and research up there. So we're packing in for about 3 days, and this was on one of the moraines is where we're moving in. So now, it's a great time to take students out in the field.
I just have to comment on the fact that growing up, you were so exposed to the outdoors, and you are 100% paying that forward right now because you're bringing these students out into the outdoors. They may never have an opportunity to do that, but you're taking them out and you're teaching them and you're exposing them to what it is like doing their study, but in the real world out there. That has got to have an incredible impact on them. Is that true? Have you found that to be true?
Absolutely. It teaches you so many skill sets. Besides putting your classroom work to use in a real world setting, which is what we want to do. We want to make those connections between what we teach and then how you learn it in the field. And being in the field is just such a different type of learning because it's also 3-dimensional. You have to see the world in 3D. And also for many of these students, they haven't been to the mountains. They may have gone to a field camp, but this is also a lesson in self-reliance and taking care of your neighbors. And you only go as fast as the slowest person. It's not about getting to the top of the mountain fast enough. Now, of course, we can all do that, but we don't. So it teaches them how to work together in a very, very tight community, because when you're camping and backpacking, as you know, it's a lot of work. We're out in the wilderness. We have to wash all of our dishes. We have to hang our food so the critters don't get it. It takes a lot to cook over a little space stove and have edible food. So, you have to, and you have to pump your water to make sure it's clean. So it's a lot of self-sufficiency. It does take determination, but they're so excited when they realize they can go from sea level to 10,000 feet, they can collect the rock, and we carry them out on our backs. So every one of those samples means something.
That is super. Now, Barbara, you are a competitive racer. You are a competitive runner. You had made a reference earlier in this interview about running and people knowing your age. But I can't help but think that those disciplines come into play when you are teaching these students. I mean, you had mentioned it's not a race to the top. So there's a certain part of you that understands that competitive race, and you have to pull them back a little bit. And I'm sure that there are times where they're going from sea level up to 10,000 feet where they feel that they can't make it. And you've got to give them just the right amount of encouragement, probably drawing upon your racing experience. How true is that?
Oh, you're absolutely right. You're very perceptive. So it's true. We do train ahead of time. So I get the students in its best shape that I can. So we go out, we practice. We used to practice in the stadium, but LSU won't let us run stadium stairs anymore. So we have trouble finding heights down here, but we run stairs when we can. But it's absolutely true. But we make sure that, you have to eat properly. You have to be well hydrated, as you know. Right. And all of that comes from some of the long distance racing that I've done. So now I don't really competitively race, but I've done a lot of very long races, the 500-kilometer nonstop adventure races. So that also teaches you, how to hydrate, how to eat properly, how to keep going at, it's the rabbit and the hare issue. It's keep going, make it to where your end point is. It doesn't have to be fast. You just need to make it. So they're usually great. I know now when to stop, when to move, how to. So it's been a learning experience, but I think it's pretty easy to see as you know.
Well, in the intro, I made reference to you having impressed me from the first moment I met you. I can't imagine how lucky and how fortunate your students are to have a teacher such as you that has incredible knowledge of the material of geology, can take them on these incredible field trips, and it's like physical training at the same time. This is like, it doesn't get better than this.
Well, I have to stay in better shape than my students, and you do know that they're like generations younger than I am. So
I know, I hate those young kids. I have to
find some way to stay in shape for the field.
Now, Barbara, it's not only in the U.S. that you do these. This is a shot of you out, I believe, on the island of Elba doing field work. Isn't that correct?
That is correct. So we were very fortunate to have gone to Elba with Federico Pizzotta. And we are here looking at, I think this is on the tip of the island. There's the Ilvaite locality as well as Elbaite on the island. So two type specimens or two names of minerals come from the island of Elba. And we're there with several other geologists. And this was a year after the Tourmaline Conference, which, by the way, is supposed to happen in 2025. So mark your calendars for another Tourmaline Conference.
Where in the world is the 2025 conference?
Currently, it's supposed to be in Madagascar. So I'll give it a plug. I was going to reach out to Federico to make sure it's happening. But
oh my God, that would be an incredible journey.
It was. And I was very fortunate to go with him on the pegmatite field trip to Madagascar in 2001, which he carefully organized at the same time as a full eclipse of the sun in Madagascar. So that was a phenomenal experience to look at yellow feldspars and all the tourmalines that were there.
Superb. Now, I've got a slide up that, excuse me, I think I'm trying to sneeze, that kind of goes into the research side of some of the stuff that you do. Tell us about this slide and what we're looking at.
Okay, so now we're going to transition to actually looking at the chemistry of some of the tourmalines. So we've done a lot of work on tourmaline, as have many people across the world. And some of the work that we're currently doing is on hydrothermal tourmalines or tourmalines from geothermal systems. And what you're seeing is on the left are the titanium contents of two different sectors in a tourmaline crystal. So tourmaline can have sector growth, and the different sectors have different compositions. And these have been calibrated as a function of temperature. So on the left side, you can see that the yellow line and the blue line are further apart, and then they're closer together, and then they're further apart. Those differences in compositions can relate to the temperature. So on the right side of the diagram, you see, again, the same quarter rim traverse of a single tourmaline crystal, where it starts at the core before the mineral begins to grow. You can see where it starts to grow and it decreases in temperature. Then the tourmaline crystal increases in temperature up to a peak, and then it begins to decrease again. And those temperatures are calculated based on the differences in the composition between those sectors. So we can see the true thermal history of this tourmaline in a geothermal system.
And so
that makes sense?
Well, I'm grasping because I'm not scientifically minded like that. What does this tell us about the environment or the growth of the crystal itself?
So the crystal itself, it started to grow at a temperature of about 300 degrees. Then the temperature in that system decreased to about 290, and then the system heated up again. So it's a second thermal pulse that happened in this geothermal system. So the temperature then increased up to about 330, and then the system began to cool again. So we know we can take that tourmaline composition, relate it to temperature, and then relate that to the overall thermal history of the geothermal area.
Now,
so this provides.
No, go on, please. Yeah.
This provides us with a single mineral thermometer to understand how that geothermal system evolved.
Now, this is the
next
part
picture,
that. I'm sorry, go on.
The next picture shows that crystal, I believe. Sorry.
Okay. Oh, no. Whoops, sorry. This one.
That one. Perfect. Thank you so much. So on the left, you see a picture of the tourmaline down a microscope. This is called plain polarized light. It's just a very thin slice of a tourmaline, about 30 microns thick. And you can see it's slightly darker orange. It looks like a V. So that's a sector of a tourmaline. And then on the right side, we see this same tourmaline crystal, but now using one of our machines that we'll look at in a little bit. And this is called a backscatter electron image. And it shows basically the mean atomic weight of that individual area. So the darker lines, the darker areas are lighter, and the brighter areas are heavier. So all of these little dots are the places where we analyze the crystal. So and we use the crystal, which is in the center here in the V, and we match one of the bands to the side where it's the same band, but on a different sector, and that gives us differences.
Fantastic.
So that's some of the work we do. We primarily use very highly precise and accurate chemical data of our tourmaline to understand the evolution of geologic systems.
Now, Barb, this brings me back to one of the great memories that I have of you was, I believe the year was 2013, and you were giving a presentation at the Dallas Symposium. And my big takeaway from that was and this kind of exemplifies it, was your comment that tourmaline becomes a incredibly effective diary of what the earth is doing. And that just kind of blew my mind. But I mean, it's exactly what you're showing here, those changes in the temperature dictating what is going on in the earth.
Mm-hmm. So tourmaline is amazing in that it has a very complicated crystal structure, but that allows it to incorporate a wide variety of chemical elements, most of the periodic table from -2 to +4 in valence state. And it's very, very sensitive to the environment in which it grows. So it can record, as you could see, the temperatures in which the environment is, and it can also record pressures. But once this chemistry gets embedded in the tourmaline, it doesn't change. So you could see those very thin bands, the chemistry, it doesn't diffuse, the elements don't diffuse. So it basically holds that chemical fingerprint as a signal for us to decode. So as you said, we had dubbed it a geologic DVD because once it embeds that signal, then it retains that signal. But of course, when we started this work, we called it a tape recorder.
Well, technology is changing. Maybe DVD is a term that we need to update anyway. Okay, I'm going to go along this line with tourmaline, and this next image is the start of a story that's really important that relates directly to you. So describe to our viewers what we're looking at here.
Here you are looking at a locality in the Apuan Alps near the Fornaso volcano. And this is a metamorphosed rhyolite. To the left of the waterfall and also to the right, it's kind of coming down a fault. And in those metamorphosed rhyolites, there are biotite crystals that have reacted to form tourmaline. So there was some infiltration of boron. The biotite was breaking down. Biotite contains a lot of titanium. And when it was breaking down, there was no other mineral for the titanium to go into other than the tourmaline. So it formed a titanium-rich tourmaline, richer tourmaline.
Super. Okay. And then this is a very prominent young man in this part of the story. Introduce us to him, please.
So please meet Christian Biagiani. He's the discoverer of the titanium-rich tourmaline that he generously named Dutrowite. So he, together with his colleagues, Ferdinando Bozzi and several others, found this new species of tourmaline, and they were so generous to name it after me. So he took us 2 years ago, he took us on a field trip to this locality, and there we were collecting tourmaline. So that's a sample of the metarhyolite that has the dutrolite in it, and here's a sample that I brought back with me. So that was Christian.
Oh wait, let's hang on. Let's hold that up if you wouldn't mind, and we're going to cut back to it. There we go.
So here we go. So this was fantastic. So he was so generous to take us up, and we were able to collect as much as we could and carry back.
As much as you could pack out.
Exactly. And fortunately, we had it sent back. It was a little too much for the suitcases.
Sure. Okay. So this is actually what dutrolite looks like.
It is. It's the brown mineral to the left. It is dark in color. It's a enhanced specimen. It looks quite dark brown or black. And the DTW is the official IMA abbreviation for dutrolite. So that's the dutrolite on the left, and then it occurs with dravite also.
Superb. And so I'm going to cut in straight to the photograph there so that we can get a better view. And so all this brown is what we're looking at, right?
That's correct. Mm-hmm.
Yeah. Well, congratulations for that. I mean, it's so perfect that you have a mineral named after you now.
It was so surprising, and of course, it's a deep honor. They called, or I found the email. It was just before Christmas in 2019, so it's hard to match those types of Christmas presents.
Oh, totally, totally.
But
Fantastic.
it was absolutely fantastic.
Now, Barb, our viewers, I've told you before that our viewers just love when we talk to researchers, and you are certainly not an exception. I've been seeing some really great comments in the chat about you. But you have a camera there, and you're actually not in your office. You are in a temporary room that you've lovingly decorated just for this show. When we did our test run, there was just a blank wall. But you're next to the lab, and so you're actually going to take us into the lab now. So if you wouldn't mind, let's grab that phone. In the meantime, Raquel is going to go ahead and launch the poll. And Barb, you could ignore what comes up on the screen.
Okay. And I will walk into the lab.
Okay. And we're going to cut over. We're going to spotlight there we go.
I can't actually see anything because I just see the questions, but that's okay.
Okay. Well, you're not allowed to read the questions.
Okay, I won't. I promise. I like these. They're very fun. Okay, so all I see currently is the poll, but that's okay. Can you see me?
Yes, we can see you and we can hear you.
Okay, great. So we're now in the electron microprobe lab. And as we saw earlier, much of my work involves highly precise and accurate chemical compositions of minerals. And one method that we use, and basically the primary method we use, is electron probe microanalysis. And this is our electron microprobe. And it's a variety, well, it's made by Joel. So we have lovingly named it Jolene. And if you are nice to the microprobe, it works really well.
Treat her nice, and she'll treat you nice.
Yeah, so there's a lot of background noise just because of the vacuum pumps and things. So I'm just going to briefly explain the components of the microprobe, and then we'll look a little bit more at how it actually functions. So this is basically what we call a column. It's where electrons are generated and flow down. Back here, these instruments, the columns are called a spectrometer. So we have a 5-spectrometer machine. Those all have a variety of crystals in it, which we'll talk about. We have other types of detectors on this. We have an energy dispersive spectrometer. We have an optical microscope, so we can actually focus the minerals. And then we have a cathodoluminescent spectrometer also, so we can see the visible light that's given off when the electron beam impinges on the sample. This is also the sample holder for our specimen. So basically, what we use to analyze, and one of the powerful components of the electron microprobe is it allows us to get chemical analysis in situ, meaning that we know exactly the place on our mineral that we're analyzing. And it requires the use of a thin section, which is, again, about a 30 micron thick slice of your rock. And this has to be polished to a very high polish. It looks like glass. If you hold it up to the light, it'll shine at you. And we need that very flat surface to maintain the geometry that's needed for these very precise chemical analysis. So the way our microprobe works is we'll put either our thin section or a grain mount into the sample chamber. There's a vacuum lock here because it has to be under very high vacuum. Otherwise, the air will impinge on the electrons that are coming down.
Okay.
They're coming down the column. So here's our lock. We put our sample in. And then what happens is we shoot a very high voltage beam of electrons at our sample. So in here we have our electrons are generated by a tungsten filament, and then they're accelerated down the column, and they can be focused by some electromagnetic lenses. So you can focus it down to, about a 2 micron beam size, or you can raster over the sample. So what happens is once the electrons impinge on the sample, it can, for the many elements in, let's just say, tourmaline, it can knock one of the inner shell electrons out of the element. Then an outer shell electron will fall in, and at the same time, it will release an X-ray wavelength or photon of energy. So that we set each of these spectrometers to specifically reflect or diffract that characteristic X-ray that's given off by the element. So, for example, magnesium has one characteristic X-ray wavelength, and iron will have another. So we have to analyze each of our elements in series. So we'll have those X-rays counted here, so they're diffracted by the crystal, and then that sends it to a detector, and then they're basically counted. There's counts per second. And those counts per second are then translated to the intensity of the counts per second are translated to a concentration. So we can analyze, because we have 5 spectrometers, we can analyze 5 elements simultaneously. And each of them, again, is set to for specifically one wavelength of an element. And we usually analyze 13 to 14 different elements for a typical tourmaline analysis. And
so then, Barbara,
in order to make that transition from counts per second to concentration, we have to standardize those elements ahead of time. So we have standards of known concentration, and we, again, relate the counts to the concentration. And
so then,
as you might know, we have an excellent analytical setup for tourmaline analysis. We have great standards, so you need a lab to do tourmaline analysis, we're it.
So, Barbara, this isn't so much for identification, because to calibrate it, you need to know what the mineral is, but it's for detecting variations. Is that accurate?
That's correct. So typically, we can actually, I'll back up. Yes, we need to know what the mineral is prior to analysis and what the expected elements are that occur in the mineral. So for different compositions of tourmaline, we know we'll have different chemical elements. So we'll set up and standardize on those elements prior to analyzing the mineral. And it's true. So this is primarily used for major and minor elements. We have detection limits down to ppm, and we can analyze, for example, titanium and quartz, which also is another way we can get at temperatures.
Okay.
But there's the energy dispersive spectrometer here. If we can step over here for a minute. So these are all called wavelength dispersive spectrometers, but we can also look at an energy dispersive spectrometer. And this, if you can come up, yeah. So this actually is it shows counts of the elements per energy, and this will give us the energy. So the energy and the KeV that each element comes off. So this is a fingerprint of the mineral. So it's just a quick and dirty analysis. So we can tell, oh, look, it's got all these rare earths. it's got phosphorus, and it's got oxygen. So we know this is a monazite. So if we're trying to look around the sample, we could actually see what it is. If we could just do a quick and dirty. This takes a couple seconds, where we typically count on each element for anywhere from 20 to 40 seconds when we're doing wavelength dispersive spectrometry.
Barb, turn back the clock. During your PhD time, were there similar instruments available, and at what size and cost?
Yeah, there were, but it was much, much larger. And the way we can use this instrument now is you can set maybe 200, 300 points. You just move from position to position and program all of those points in. During my PhD, it was a much different experience because, well, first of all, it was twice this size. The computers were very different. You didn't have all of this interface, which is fantastic. So we had to position the beam on the sample and then hit the go button, analyze. Then you'd wait 7 minutes, and then you'd move to the second spot and hit analyze again. So it took you all night of sitting there, moving, hitting the button, and moving again.
Gotcha. And this is the machine that did all those red dots in that slide that we brought up earlier, correct?
Right. So that was actually, again, a backscatter electron image. And if we look here, we can see another backscatter electron image, and you can see the color variations. So we can set the beam to be on each of these different zones in the mineral. So we can see exactly where we are, and we can change the magnification. This happens. So here is our backscatter image. I don't know if you can see this. This is our secondary electron image, which again shows the surface morphology. You want to avoid any pits or things like that in the sample. So we always look at that and make sure that it is focused, because that's required for the geometry of the system. And then we can also see within our thin section where we are. So this happens to be, looks like a brain kind of. This is a thin section. These are all basically tourmalines. And then this is and that's just in plain polarized light. And then this is our very small tourmaline that's basically right there. So,
wow.
So we can, and every year when I go to Tucson, Alfredo Petrov always finds me just amazingly interesting minerals. And this happens to be one that he said, "What is this? I think it's a dachyite." Well, it's not. It turned out to be dravite, but it's still a remarkable specimen in its complicated growth history.
I love it. That is fascinating. What other kind of research equipment do you have there in the lab?
Oh gosh. Well, we have a lot. So let's see, were you also going, I realized we're out of time, but I also wanted to show you this. Brian, do you remember?
Oh, this was in response to my question. What was the weirdest thing that you ever analyzed that you maybe shouldn't have analyzed? I was expecting an answer like a bologna sandwich, but you told me like a really great story. So go ahead and share it with the viewers.
Sorry, if I can just quickly. So again, we have this 15 kilovolt beam of electrons, and I had found at Tucson some colorless tourmaline, which are quite unusual. So we mounted them in this material called crystal bond, which I've used in ion microprobes before. So it's very stable in a high beam. We put it in the machine with these two beautiful cut colorless tourmaline gemstones. And then all of a sudden, you could see nothing. You could just see the electrons building up on the surface. And then all of a sudden, it went blank. And it turns out that we exploded the tourmaline and the crystal bond in the machine. I'm pretty sure it was not tourmaline. And then, because it's under such high vacuum, we had to completely shut the machine down for like 2 weeks, clean the column, and I'm sure that was not true. So,
and we never did figure out what it was, right?
No, I'm thinking it might have been, I don't know, Danberite or something, but I don't know how you mix up those two things. So we have a carbon coater over here. Each of because most minerals are electron insulators, you have to put a conducting surface coating on the sample. Otherwise, it'll just build up. And so we use carbon or gold, and this is our carbon coater.
Okay.
And then we have various scales and presses, and we have an X-ray fluorescence unit, and we have an X-ray diffraction unit, and things like that.
Amazing.
So now, I realized it's going too fast, and I don't know if you want to see I just want to show people that even though I live in a mineral challenged state, that we do have a mineral display. And so if you've ever given me great deals on minerals, my students and I thank you. And please remember to do that in the future. So these are some of our minerals that are from one of our collections. This is an alum who gave us some nice minerals. So we have these for teaching, and then the nice minerals that I show students in mineralogy class.
I'm sorry, tell me again who gave it to you?
It's William Blake. It was one of our alums who went on to be a very, who went on to be an oil and gas man. We have a lot of those in our department.
Well, from a fellow mineral poor state, I appreciate that exhibit.
Oh, but you actually have minerals. We have salt. You know, I used to take my students on a monomineralic field trip. We could go down. We went down in the Avery Island Salt Dome, which is, by the way, where the Tabasco peppers are grown.
Oh, right, for the Tabasco brand hot sauce.
Yes, they grow on salt domes, so that's why they're from Louisiana.
Really?
Yes.
Oh my God!
You never know how useful minerals are in many ways.
That is superb. I love it. I love it. Okay, Barb, we are at the point in time where I'm trying to be very conscious of the time that we have left, and we're at the point where we are exactly 1 hour into the show. So I'm going to do the quick fire 5 questions right now, and then I'm sure that we have a lot of questions or Q&As from our viewers, and Raquel will take over that point. So this is quick fire 5. So I have 5 questions here. There are 2 answers to each question. You share with us which answer you resonate with most strongly. All of your answers are correct. We're seeing if the viewers correctly predicted how you would answer. Are you ready?
I'm ready.
Okay. Actually, before I start, I've got one last question for you. LSU has, from what we're seeing, an incredible research laboratory, very strong in geology. How does that rate with other schools that have a strong geology program? It seems like the program there is outstanding. With you as a teacher, it's undoubtedly outstanding, but give me kind of a rank in there with your university and other geology universities.
Oh, that's just really dangerous.
Oh, okay. Let's do we walk on the line of danger?
Pardon you?
Do we walk on that line of danger, or do we go straight to the quick fire 5?
Yeah, let's just go to the quick fire 5.
Okay, well then let me speak for you. That has got an excellent program there, one of the best.
We have a great program in some areas. Different geology departments have different strengths, and we certainly have a strong group in I think hard rock geology. So I tend to, we have a good strong group there too.
Superb, love it. Okay, quick fire five. You are ready. So, and I guess the poll that came up were the questions, so everyone's already seen this. So, question number one: favorite type of mineralogical work, field work, or lab work? Ooh, that's a tough one. I didn't think it would be that difficult.
Oh, I'm going to go with field.
Field work. Okay. All right. Favorite barbecue, fish or steak?
No question. Fish. I grew up in Nebraska. Fish. I don't eat meat anymore.
There you go.
Fish, definitely fish.
Okay. Favorite thing to do on a free weekend, long distance running or attending mineral shows?
Oh, come now. The best part about Tucson, it was right before the Boston Marathon, so you could always do long runs along the Rito River. That was very handy.
Nice.
Oh, well, I don't have any mineral shows down here, so I'm going to do running.
Long distance running. Okay. Favorite drink, beer or margarita?
Oh, well, that was easy. Margarita.
And your favorite thing to wear, a tourmaline cutstone or a tourmaline crystal? Ooh, that's a tough one.
That's a tough. I'm going to go with cut.
With the cutstone.
I'm going with cut.
Okay, before we get to these, I want to mention that there was a comment made by Catherine Jensen, and I don't know if she's related. I suspect that she is, but she commented that the pendant that you're wearing is a Michael Jensen design pendant. It's not?
I hate to say this, but this is a cut black tourmaline. It was cut by John Bradshaw because after Dutrow, it's probably black. I wanted a cut stone. And then this pendant was designed by, together with a mineral designer or jewelry designer by the name of Valerie Fairchild out of Santa Fe.
Okay, I think she did mention Valerie was involved in this. So yes, okay. So it is it is the same. Okay, wonderful. Raquel, are you ready with the answers to the responses from our viewers to the quickfire 5?
I am.
You are. Okay. Question number 1 was favorite mineralogical type of work, field work or lab work. After a little bit of deliberation, Barb went with field work. What did our viewers say?
90% of the viewers said field work.
I think that would have been obvious based on the background that you have there. And yeah, that's superb. Okay, question number 2, favorite barbecue, fish or steak? With a look of disgust on her face, she went with fish because she doesn't eat meat anymore. What did our viewers say?
Somehow 71% of the audience also knew she was more a fish person.
I love it. Super.
I do eat some meat, just not a lot.
Yeah. Okay. Question number 3, favorite thing to do on a free weekend, long distance running or attending mineral shows? I actually was surprised by the answer here. I thought we were playing to the cheap seats here, but Barbara went with long distance running. What did our viewers say?
Long distance running, 3 out of 3 so far.
Nice. Nice.
I am so not a mystery.
Okay, favorite drink, beer or margarita? This was a no-brainer. Of course, margarita. What did the viewers say?
Same, margarita.
I love it. I love it. And then the final question, favorite thing to wear, tourmaline cutstone or tourmaline crystal? And Barbara ended up saying cutstone. What did our viewers say?
I'm going to cry. People said tourmaline crystal.
Oh, okay. Well, 4 out of 5 is not bad. It's been a long time since we've had a 5 out of 5. So that is not bad at all. We're going to go into the Q&A. Excuse me. We're going to go into the Q&A. And there is one more question that I have for Barb. So if it's not addressed in the Q&A, I'm going to do a follow-up question at the end. So Raquel, why don't you take it away and let's do Q&A.
Okay, so I guess I'm gonna go in order. Let's see how it goes. So one of the questions, we have a few people commenting on your necklace. I think now we got it all. I just want to know about the rings. So, but do you wear just tourmalines, or you also wear other type of mineral jewelry?
Oh, I do wear other stones. One of my favorites is emerald, of course. But I
Nice.
do wear other types of stones. I will have to tell you, I dressed, as best I could. I was telling Raquel that I dress like the mineral I teach. So often, I need to dress for things. So this is a chrome vanadium tourmaline. This one.
Beautiful.
And we've actually, tourmaline, as we said, is an amazing geological recorder of geologic conditions. So we've actually analyzed this, and we know that it has the color is caused by vanadium and chrome. It has about 800 parts per million vanadium, about 400 chrome. And through partitioning experiments with fluids, we know that the fluids it grew in had about 5 parts per million each, chrome and vanadium. So I'd like to know the compositions of my gemstones too.
I love it.
That's so impressive. I love it. One thing, Brian, it hasn't come on the conversation, and I also want to make a point. Barb is the only researcher scientist on the board of GIA, the Gemological Institute of America, and I'm really pleased to see that there are researchers out there that see gems as what they are, the essence of the minerals. There is so much information you can get out of a gemstone, sometimes even more than out of a mineral. So I'm really pleased to see that you are on that board and really pushing that field.
That's perfect. That was the one question I was going to talk to her about if it wasn't brought up in the Q&A, and it was. So perfect. Thank you.
Sorry, I had to say, and I wasn't sure if you would, but anyhow.
Oh, I love it because you've got this real kind of like rough, husky voice right now, and it's we want to hear more of it. So keep going.
Thank you. So let me carry on. We have a question now by Jean Myron. The tourmaline example was a horizontal section, right? Is there a longitudinal section that shows similar temperature variation?
Sorry, could you repeat that?
No, yeah, I guess it goes back to the section that you were showing on the map. He thinks that was an horizontal section, the analysis. And he was wondering if you also did a longitudinal, so changing the direction of the crystal, if it would show a similar temperature variation.
Mm-hmm. If you analyze the two sectors wherever they are on the crystal, you will still get that temperature variation. If I got the question correct.
Yes.
So that's the power of sector zoning in tourmaline, and then having this oscillatory zoning on top of the sector zoning. So because that has been calibrated, we know that difference in composition between the A sector and the C sector, wherever you measure on the crystal, you will get, if you measure the two different sectors, you'll get that temperature.
Okay, thank you. From Patrick Roycroft, do the tourmaline contain fluid inclusions? And if so, do these corroborate the temperature estimates derived from the tourmaline chemistry?
They do contain fluid inclusions. They're often quite small. I personally haven't done any fluid inclusion work, but most of the work that's been done corroborates the temperatures. That crystal was so small that it didn't have any fluid inclusion, so we couldn't collaborate or corroborate it that way. But we can by other techniques, other minerals.
From Barbara, we have 3 Barbaras today. Regarding titanium and tourmaline, does titanium create any special color or dispersion the same way that copper does in Paraíba, or is just a marketing ploy?
So depending on what and I think George Rossman is on, so he could give you a long lecture on this. But so in this case, the tourmaline or the titanium and the iron, it's black. So it's basically brown. It has crystal field effects. Sometimes it makes crystals blue. So the charge transfer, molecular orbital transitions between the titanium and the iron can create a more blue color. So it does create, usually it's in combination with other elements, but it can just create a yellow or a orange brown color also.
Thank you. So another one about the chemistry. Obviously, you got the back on everyone today. We have also Patrick asking about the origin of boron on the tourmaline in pegmatites and embedded tourmalinites. I don't know if we use that word. Does it come from the granite, or is it mobilized from the country rocks that the granites intrude, or both?
It can be both. Each different geochemical environment may have a different source. In many cases, the boron just builds up in the magmatic fluid. It's an incompatible element, so it builds up in the fluid as the rock crystallizes, and it can be internally derived. In other cases, it's definitely infiltrated from the host rocks. And if he's talking about the tourmalinites, it's a hard word to say. In many cases, those are external fluids that can come from a pegmatite, or they can come from deeper, or they can come from devolatilization of, say, a borate deposit, for example. So metaevaporites are great places to form tourmalinites because there's a lot of boron in evaporites.
Nice one. Israel, do systems with multiple hydrothermal fluids events that cause multiple generations of tourmaline growth compromise the geochemical data in other tourmalines?
No, what's so remarkable is that even in a single fiber in a tourmaline from a pegmatite, and we've done some work on these, you can see 3 different generations of tourmaline in a single tourmaline fiber. So I was going to send you one of those photos. I should have. So what happens is that if you have different generations of fluid that are slightly different compositions, so tourmaline is stable in acidic compositions, it's not stable in alkaline compositions, the tourmaline will slightly dissolve to be in equilibrium with the fluid, and then it will reprecipitate a new composition of tourmaline that's in equilibrium with the fluid. So in that way, it doesn't diffuse, but it may dissolve and then reprecipitate in multiple generations. But typically, tourmalines just don't diffuse. That's why you have those spectacular zones like the one lidocotite that is in the Harvard collection.
That is on the cover of the book of the second edition that we all use. So Israel was also one. Sorry?
Did that make sense to you?
Yeah, 100%. Thank you. They were wondering what's the best age dating method for very small tourmaline grains with a lot of alteration over printing textures.
Yeah, that's tough. Tourmaline is very good at temperatures, pressures, fluid compositions. For age dating, it's not quite as robust. So there are potassium argon methods that are being developed. And I think in our elements issue, there was a paper on geochronology of tourmaline. But potassium argon, or argon actually is probably better. So some compositions can be dated by argon methods, potentially rubidium strontium or strontium. But it's, uranium and lead. Uranium doesn't fit very well. Lead does into the crystal structure. So probably argon.
Very good. Someone on the audience throughout the chat was asking if they were saying there are 22 marine species. I believe there are more. There are over 40 by now. But
I think they're close to 40, if not.
Yeah. So he was asking more from a collector point of view, what's the best way to tell what they have found or what they have among all these species?
It's important to have chemistry or have someone who has done the chemistry, because, a green tourmaline could be a schorl, an elbaite, a dravite, fluoroschorl, oxydravite. So oftentimes chemistry is necessary.
Yeah, I guess when you get into the whole classification, but on a broader, if you want to make it broader, mainly would be elbaites, right? From a collector point of view.
And also, that's true. And, sometimes the associated minerals will give you a good idea what the tourmaline species is. If you're at Potosi in Bolivia, it's going to be provandrite or, bergerite. So, you can tell from sometimes those types of localities. But do you mean just collecting overall?
Yeah, I guess that was the more from a collector point of view. When they go to Tucson or they go to find tourmalines, usually I'm thinking, I don't have all the details, but I'm thinking they are more either collecting in Maine, so they're going to be collecting mainly elbaites.
Right,
right. Yeah.
Right. The pegmatitic tourmalines are without a doubt the most beautiful. So they're mostly elbaites or sometimes foytites.
Okay.
And the fibers can be multiple species too. The beautiful hairy tourmaline from Mexico, from I believe it's Minas Maria. Those are little dravites, little blonde hairs growing in quartz crystals. They're fabulous.
Amazing.
So those are dravites.
So George Rossman just wrote on the chat, because Barb, you don't read the chat. He wrote 41 tourmaline species now. We got it. It takes detailed analysis to really determine what it is. San Crista have 3 or 4 different species in a single crista.
So I hate to tell you this, and some of you listening may want to plug your ears, but one of my students has worked on tourmaline from the Dorothy China clay pit in the UK, and she found 8 different species in a single tourmaline.
No kidding.
Wow.
No kidding. A lot of growth and dissolution, fibrous growth. Yeah, it's fascinating.
Fantastic.
And I have one more question if we have a couple more minutes. Is there any tourmaline scepters? To my knowledge, they look so, for many people, accepted, but I believe they're just natural etching pieces. Do you call tourmaline as for quartz, we have the scepters. Do you ever call tourmaline scepters, or it will be more natural edging? What's your take on that?
Well, there are some tourmaline scepters. I think the picture I sent to you is really a tourmaline scepter.
Okay.
Looks that way. Yeah. So
is that this? This
one.
One.
That one.
Right. So it is a lot of etching, but you do have, a very wonderful pyramidal termination on the plus C, and then more the elongate growth on the minus C direction.
Beautiful. And one more question. Have you ever analyzed any Rancul tourmaline? I'm not familiar with that. RANGKUL. Rancul tourmaline.
I don't think so. But feel free to send some. I'm happy to analyze it.
Okay. So, Brian, I think that's most from my side from the Q&A question. Thank you so much, Barb. This has been a delight. Really, it was worth the waiting.
Definitely worth the wait. So we're going to sign off. I know, Raquel, you have to get going. I don't want to finish this without making one final point, and that is, Barbara, you are paying it forward to other young women in the field. These are some of your students who have graduated, who have all been influenced by you. And I just want to say, I think you are doing an amazing job. You, in our conversations, you've made it clear that you love all your students, but especially when you have young women like this who have such an incredible role model, such as yourself, doing these incredible trips, I believe you are really making a difference in what's going on out there. So I take my hat off. If I were wearing one, I would literally do it. But I take my hat off to you, and I really want to thank you for everything that you're doing and for spending some time with us today.
Thank you so much. It's my pleasure. And thank you for doing this and helping elevate mineralogy and the mineral sciences to a larger world. So thank you.
Thank you. Very kind words. So that is going to be our show for today. Thank all of you for tuning in today. Our next show is going to be our July show, and I'm going to be actually doing that live from Paris, France. And I'm hoping that Eloise will be able to join me, and we will be together streaming to you live. And Raquel, I believe you're going to be in Massachusetts for that, correct? Oh, I think Raquel left.
Oh, I think
so. Yeah, we are at the very edge of the show there. So thank you again for all of you tuning in. We'll see you again next month. Take care.